Okay, welcome to lecture 3 of our IEP class on causality. Today we'll be continuing from lecture 2, talking about policy evaluation. Lecture 2, we talked about policy evaluation in non-parametric models. So today we're going to be moving on to identifiability in parametric models. Some parametric models that we might be familiar with would be linear models. So all of these are always making some form of assumption on the causal mechanisms in the structural causal models. So a linear model would have xi be a sum of all of its parents in the exogenous augmented graph. So that's parents in G tilde, xi, and then they're each going to have some weight coefficient, beta vi xi, vi. So this is in the case of Markovian models. Going to simplify, we are just going to have one exogenous noise term, and typically we just rescale it so that this coefficient equals 0. So you'll usually see this written as, say, xj, the parents in just the causal graph for xi, beta xj, xi, xj, plus the end some epsilon I noise. So we got linear models. If our variables, instead of being continuous, say one of the variables is discrete, but its parents are continuous, then you might get something like a discrete choice model. So here we would have basically defined ui to be some utility, which is the same linear combination. And then xi is just, so that ui is like a placeholder that goes into the real equation for xi, which is say that just the utility is greater than 0. Of course, there's a bunch of other types of parametric models that people study. So you could have exponential family models, anything where the set of functions that appear as candidates for your causal mechanisms are indexed by a finite dimensional set of parameters. So our examples today are going to be with linear models. Those are particularly well studied and come up a lot in things like econometrics. So the two examples that we'll be talking about today are identification through instrumental variables and identification through proxy variables. So let's define what we mean by an instrumental variable model. So what we're thinking of is that we have a variable A whose effect on y we want to measure. In the linear case, we can summarize this by whatever the coefficient is for y that goes with A. So this beta AY, which we'll also think of as kind of an edge weight. So we'll have this weighted DAG model. And then what we're trying to do is worry about, okay, maybe these are confounded. So there's some variable z that we don't get to observe, so we can't adjust for it. That's confounding both of these. And the idea is that we will introduce an extra variable called w, which is going to be the instrumental variable. So we'll say that w, a, and y are observed variables satisfy an instrumental variable model IV model if there exists Z such that this whole tuple Z, W, A, and Y follow a linear structural causal model. With this G as the causal graph. Okay, and just to make that explicit, what this model is going to look like is that we're going to have Z equals epsilon Z, and then we're going to have W equals epsilon W. A is equal to a linear combination of Z and W plus its own noise, and Y is equal to a linear combination of Z and A plus its own noise. And then we'll do things like say all of the noises have zero mean, and we can get that by rescaling. So just subtracting off from samples, we would take the empirical mean and subtract that from samples. Most of the stuff should go through. Okay, so a couple notes on this. In the instrumental variable model, the actual instrumental variable that's what we're calling W, is the instrumental variable. And the important thing here is it satisfies what is called the exclusion restriction. And this is saying that there is no direct edge from W to Y. So you'll see that various different ways, but we'll use it accordingly this way. So this is the model that we have in mind when we're talking about instrumental variables, at least in the linear setting. And as an example, we might consider a case, kind of from the mid-century when people were having all these debates over whether or not smoking causes cancer. So what people were saying was, okay, we know that, say, smoking and cancer have this positive correlation, so people that smoke, it's more likely that they also get cancer. But all the statisticians may be aligned with the tobacco lobbies who are trying to make claims of, well, and this is true, there could be kind of confounding variables so that you can't just interpret that association as smoking causing cancer. And what they wanted to argue, say, was that maybe there's something like socioeconomic status or a gene or something that is a latent cause of both of these. And the principle behind introducing instrumental variables would be to take something else that we can measure. So say across different states, looking at the taxes that they put on tobacco, which we would expect to have some effect on smoking, probably decreasing the amount that somebody smokes because it's more expensive, but not have a direct effect on whether or not somebody gets cancer. the only effect would essentially be through smoking. Okay, and this would be the type of model where you might try to use your instrumental variable and the kind of identification result that we'll present today in order to figure out the effect of smoking on cancer. Great. So the theorem here is going to be that if we have W, A, and Y satisfying the IV model, with, in particular, we're going to need that this is in some sense a true instrument, so beta WA is not equal to 0. There's actually some effect of W on A. Then beta AY is identifiable. Okay. And we can get to this result by plugging in the equations that we have for each of our variables. So in particular, if we look at Y, and we plug in the equation for A, what are we going to get? Well, first, we're going to still have Y is beta Z A times Z, but then we're also going to get a coefficient beta Z, sorry, this is ZY, this is beta ZA, and this is beta AY. So this will be the coefficient on Z, and the coefficient on A. This is disappeared because we plugged A in. We do have still the exogenous noise for A, so we have beta A Y epsilon A, and then finally plus this epsilon Y at the end. Okay, so if we look at the expected value of Y for some particular value of W, here I forgot to plug in the term for W, right? So this is also plus beta AY, or beta WA, beta AY, W. So if we look for the expected value of Y, given that W is W, what do we get? Well, W and Z are independent. If we look at our causal graph, we can read that statement well from just D separations. Similarly, W is going to be independent of epsilon A and epsilon Y. So this is just beta WA, beta AY, W. And then if we regress X, or sorry, if we regress A on W, then what are we going to get? Well, again, the Z is going to disappear. We'll get beta WA times W, and then epsilon A has 0 mean. So we combine these coefficients by linear regression of Y onto W and A onto W, and then we can just recover this beta AY by dividing, and then we see why we need this value to be non-zero. Since this involves two linear regressions, this method of identification, when we're actually working with finite samples, is called the two-stage these squares. And just as a note, this estimator can have some problems when we have beta WA being close to 0. So we won't get into the statistical issues in this lecture, but you could read up about this. This is called the case of having a weak instrument. And basically the problem is that if this is very close to 0, then even just small deviations in how we estimate this, since we're dividing by it, will lead to large deviations overall. Okay. So the second model that we're going to consider in this linear setting is the proxy variable model. So for proxy variables, we're going to say that now this tuple of 4 variables, v, w, a, and y, satisfy the proxy variable model. If they are generated according to basically a linear structural causal model with this additional unmeasured variable z. So it's going to look something like this, where z is again that latent confounder between a and y. But then these v and w are considered proxies for z. So we don't get to see z directly, but we get to see these two variables depend only on z. So if we write out the linear structural causal model, we're going to have z is equal to epsilon z. We're going to have v is equal to some beta z v times epsilon, or times z plus epsilon v. Similarly for w, beta z w times z plus epsilon w. Then a, again, its only parent is z, so we have beta za z plus epsilon a, and y is a linear combination of z, so beta zy z plus beta ay a plus epsilon y. And again, we're going to do things like assume everything is mean 0, and we're going to need the variances in this case, so we're going to denote the variance of each of the variables with the exogenous noise terms as sigma squared z. Then we would have sigma squared v, sigma squared w, and so on. We're going to need these to be positive and finite as well. As an example, what we might consider is if we're trying to measure, again, the effect of smoking on cancer, but we're instead focused on confounding due to something like z being attitude towards health-related behaviors. That's a kind of tenuous abstract concept that we might not be able to measure directly from people, but we can measure kind of proxies for that, such as V and W being, say, things like amount of exercise that that person gets in a week. And W could be something like, the amount of multivitamins that they take daily or whatever. Okay. So once again, we're going to be able to identify beta A y under the assumptions of the proxy variable model. We're going to need both the proxies to be kind of true proxies, so we need beta zv not equal to 0, and beta zw not equal to 0. Then we're going to have that beta A y can be written in a number of ways. The way that I prefer, because it makes the connections to some other literature on identification and linear models, it makes those connections a little bit more clear, is to write this as a ratio of determinants of the covariance matrix. So this sigma will denote the covariance matrix of those variables v, w, a, and y. I won't write all of that out, but basically what we're going to do is we're going to take these 2x2 submatrices of this. So we can express this as, first we're taking the rows a, v, and the columns y, w. And on the bottom we're taking the rows, again a, v, and now the columns a, w. And if we want to write this out more explicitly, what this looks like, so this is 2x2, the determinant's easy to compute, right? It just, the diagonal entries times each other, so that's AY, sigma AY, sigma VW, minus sigma AW, sigma VY. And on bottom, we're similarly going to have sigma AA, sigma VW, minus sigma AW, sigma VA. Great. So we'll proceed similarly as in the case of the instrumental variable model by plugging some of these equations in. So the one we really need to do is express y just in terms of z and a. So, right, if we plug in a equals a linear combination of z plus its own exogenous noise term into the equation for y, what we're going to get is that y equals beta zy plus beta za beta ay times z plus beta ay epsilon a plus epsilon y right? And then if we start looking at all of the covariances, there's 6 covariances involved in that. So which ones do we need? Let's start off with some of the easy ones. So sigma VW, the only thing that they share in common is their parent Z. So their covariance is going to be in the form beta ZV, beta ZW, omega Z squared. Similarly, if we go down the list, we have things like the covariance between B and A. It's beta ZB, beta ZA, sigma Z squared. Covariance between A and W, beta ZA, beta ZW, sigma Z squared. The one for B and Y, so the ones including Y are going to have these terms involved, so they'll be a tiny bit more complicated, right? So in this case, we have Z, Y, the covariance between V and Y, sorry, will be beta ZY times beta ZB plus the second term beta ZA beta AY beta ZB. That's all times this sigma Z squared. Okay, we have 2 more. So what we're missing is the sigma AY, which is going to be, now we have the beta ZA multiplied by all of these terms. So we'll get beta ZA beta ZY plus beta ZA squared beta AY. That's all times sigma Z squared plus, in this case, we have additional covariance coming from this. So that's going to be beta AY times sigma A squared. And then plus, yeah, that's it. Okay, and then the covariance of just A, the variance of A, yes, is sigma Z squared beta ZA plus sigma A squared. Right, so usually you wouldn't want to write out all of these derivations by hand. A lot of these, actually all of these, right, can be derived by what's known as the track rule for either DAG models or ADMG models more generally, which will tell us what, in a linear model, the covariance is between 2 variables based on some paths in the graph. And you can kind of see the form that those paths are going to take here. So between V and Y, say, all of the kind of paths that contribute covariance to them start with Z being their kind of common ancestor. And then there's the path from Z to Y, and that's inducing some correlation because we also have a path from Z to V, and then there's the path from Z to Y that goes through A, so there's the ZA and then AY, and that's times this beta CV. But you can also just plug things in and write the same conclusions, so we don't need the full strength of the Trek rule for this result, and we won't cover that. Great, so now what we want to do is just plug these into the formulas that we have up there. So let's start when we are multiplying. First, AY times VW. So we have this term and this term. And what we're doing is subtracting off the term where we're multiplying the AW times the BY. Okay, so we won't write all of this out, but just say the numerator here. A lot of these terms are going to cancel. So we have a sigma z to the fourth term, kind of with most of the things. And in this case, we're going to have zv, zw, za, zy is going to be one of those terms. zv, zw, za, zy, right? And then we're going to have here, one of the terms that cancels out is this zv, zw, za, zy. Okay, so we don't need to write that out. Another term that we're going to get is this za squared ay times the cv, zw. Again, when we multiply these, that just cancels it out. We get similarly the za squared and these two za's, and then the ay and the zv, zw. Okay, so the only term that remains is going to be this final term times this guy here. So we're going to have the numerator is equal to beta zv, beta zw times beta ay. And then we have sigma a squared, sigma z squared. Okay, and then similarly, with the denominator, the terms that are going to be involved are first the AA term and the BW term. So there is the AA term and the BW term, and then the AW and VA term. Right, and something similar is going to happen. So we're going to get, let's keep track of all of our sigma z to the fourth ones. We're going to have beta za, sorry, this is actually beta za squared. So we're going to have beta za squared times beta zv, beta zw. And then we're going to look at the other one. And we end up subtracting that, right, beta za squared, zv, zw. So the only term that we're going to have left is sigma a squared times all of this, which is just beta zv, beta zw, sigma a squared, sigma z squared. And we see immediately, like now if we, under our assumptions that these are not zero as well as these, then the denominator is not zero, we can divide. Everything cancels out except for the beta ay term. Great. So I'm just going to end with notes on some additional readings that might be of interest in kind of the space of policy evaluation. So first, I want to point out that especially with things like the instrumental variable and the proxy variable models, they are very well studied, and in many cases we don't even need parametric assumptions. We need some form of assumptions, but we can get by making things nonlinear, not even non-parametric. So there's a lot of great work on that, and there's some references in the lecture notes. Further, if we are dealing with linear models, but we kind of want to generalize in a different direction from these IV and PV models, so instead of generalizing in the direction of making them more complicated but keeping the graphs the same, we could go into the direction of making the graphs more complicated but keeping it linear. So there's a lot of work on identification in linear models. I have some readings in the notes on kind of sufficient conditions where you can input a graph, say what coefficients you want to identify, and it can tell you whether those are identifiable and give you an identification formula for identifying them. To the best of my knowledge, those are just kind of sufficient conditions, not necessary conditions. So if the algorithm fails, it does not mean that it is not identifiable. It is just not one of the types of things that the algorithms can identify. I think there is one necessary condition out there, but it's not necessary and sufficient, so there's still kind of a gap between the necessary and sufficient conditions for identification in the linear setting. And finally, a big kind of piece of the literature that I unfortunately had to skip is more of the statistical side of the policy evaluation questions that we've addressed here. So we've talked about identifiability, which is a question of what you can do when you have an infinite amount of data, when you have kind of access to the true data generating distribution. Of course, in practice, we never have that. We just have samples from these distributions. And you have to kind of convert these identification formulas into actual estimation techniques and algorithms to identify, to estimate instead of identify things from your data. And there's a lot to be said about that. What I'll start by saying here is that the kind of natural thing you might think about doing is, okay, you spit out one of these identification formulas, say something like the adjustment formula when we were thinking about this graph or graphs that satisfy the backdoor criterion. So it spits out something like, oh, what you want to do is sum over possible values of S and look at the probability y given A equals A and S equals S times the probability S equals S. You might think, well, great, I have a formula like that. What I'm going to do as my estimator is I'm just going to estimate each of these probability distributions, and then I'm going to plug the estimated ones in. This would be called the plug-in approach. And in the setting of like linear models and parametric models in general, if you're actually, so you wouldn't want to technically be estimating these, you would want to be estimating the parameters of your graph, so you would want to develop estimates of things like beta A hat, beta hat AY, beta hat SY, whatever it is, maybe tuples of parameters if you have more complicated parametric models. And then plug those in to get these estimated probability distributions and use exactly this adjustment formula. Then this plug-in approach, kind of by classical parametric efficiency theory, is going to be what we would call asymptotically efficient. So this means that it is going to have lower variance, at least asymptotically, as the sample size goes to infinity, than any other estimator. So this is in the parametric setting. And this is if we are using MLE, maximum likelihood estimation. Right. Then plug-in plus the MLE is efficient. However, in practice, even more and more nowadays, the things that we want to estimate here, we no longer want to use as parametric settings. Say that S is some super high-dimensional variable, say even like an image of somebody's tumor, that's going to help us decide what treatment we give them, but well, the image itself might not affect the outcome, but the kind of underlying thing that's generating that image is affecting the outcome. And then this probability distribution over S is going to be super hard to estimate. This is going to be super hard to estimate. We might do something like fit these probability distributions using a neural network or Gaussian processes or other kind of non-parametric estimators. And then this plug-in approach can break down. So that's a big thing that people pay attention to in practice when they're estimating with these kind of more expressive model families. Then you have to use different techniques so you can modify the identification formula to get a new identification formula that still identifies your quantity in the case of the population setting, but has better guarantees statistically. And that is a big focus of what could be called semi-parametric efficiency theory. Or also double machine learning, which is abbreviated DML, targeted maximum likelihood, orthogonal statistical learning. These are all similar names for this set of ideas, and there are some references for that as well in the lecture notes. So thank you. That concludes the section on policy evaluation, and in lectures 4 through 6, we're going to get started by talking about causal structure.